All right, this is on the homework problems we just messed up on. So make your corrections on a separate sheet of paper and then turn in your corrections with the original worksheet. So in this question, the first question people kind of struggled with was, how do we do the simulation-based test of significance? What is that? Well, the first thing is that you'd have to fabricate a large data set to represent the population of times for all Cal Poly students with variability similar to the sample data. So the standard deviation is going to get pulled from the 100 sample, but the mean is going to be the population mean. And the way, it's a computer algorithm that does this. And so the way you do this is you create random people and you place them where you know they should be placed under some assumptions. So you make some assumptions of, you know, what one standard deviation or two standard deviations away from the mean actually means, and then you place them there. That algorithm is complicated, and so we're not teaching the algorithm this semester. If you take more math, you'll have to learn how to run R to get that algorithm. But anyways, we have an algorithm that can fabricate a large data set that has the mean of the population, so it's a null. It's the null hypothesis distribution. It's a distribution that goes with a null. And we can't do a flipping of a coin exercise to do this because these are quantitative variables, so we can't do that. So we need a computer algorithm, and once we know the mean and standard deviation, we can create that. And I mentioned before I did this with data people wouldn't share because they wanted to hold on to it and write papers, and so then if I know the mean and standard deviation, I can make you that null distribution. So that's how that's done. So now we have the null distribution. Number one gives me that null distribution. Number two, from that null distribution, I'm going to take a sample of 100 and find its mean. And in a spreadsheet, I'm going to record that sample mean. Again, from the null distribution, I'm going to do it again. Take 100 out of that null, some random 100 out of that null distribution. Each one of the dots in that null distribution represents a person. A fabricated person, and I'm going to calculate its sample mean. So I'm going to do this 1,000 times, and then I'm going to graph the frequency of those sample means in the bins. Remember I told you the dot plots are plebes in a bin? In the same way, each of those sample means is going to fall somewhere, and I'm going to put them in their appropriate bin. And that's going to give me, if I took a random sample of 100 people, what would their mean be like? I'm going to count, so this is going to give me a distribution, a dot plot made out of sampling 100 people from this big fake data set. Once I get that distribution of sample means, so 100 gets pulled out, I record its mean. Another 100 gets pulled out, I record its mean. I keep doing this 1,000 times. That's going to give me a null distribution to benchmark. And then I'm going to count the percentage of simulated dots that are at least as far away from 2.75 as that of 3.01. And that's a really weird sentence to say, but I need the p-value, and it's a two-sided p-value because my alternative hypothesis was that mu was not equal to 2.75. So since it's two-sided, I'm looking at distances away from 2.75. And so I'm just made a little diagram here. So this distance here from the mean to where I need to cut off from is going to be 3.01 minus 2. That's the distance. And this distance right here is also going to be the same distance. And I'm counting the number of dots that appeared in this yellow area, the percentage of total dots that ended up in this yellow area. And that's my p-value. And that's how I do the simulation-based test of significance. So those are the steps. This data confused people. What they want here is what one repetition means is I have the fake data and I sample 100 from that fake data and calculate its mean. That's one repetition. And of course I do this 1,000 times. So they want this, what does it mean to do one repetition? The null model in my case would be mu is equal to 2.75. Greek letters are always used for parameters. My statistic is x bar. It's the sample mean, which ended up being 3.01. All right, so a big thing is what the p-value means. In 2.2.13, they said the p-value was 0.16. What does the p-value mean? Literally, copying and pasting from a definition of p-value. The probability we would get a sample mean as extreme as 3.01 from a random sample of 100 students is 0.16. That's a two-sided definition of p-value. Or you can, some people use just this. It's the amount of dots that is distance 3.01 minus 2.75 away from the mean, that proportion of dots that ended up on both sides. You can explain it that way as well. That's the p-value. The p-value being 0.16 is not good enough because in a table we have levels of significance or the strength of the evidence. P is less than 0.05 is the first place that I have some evidence for rejecting the null hypothesis. So this is the probability that we use to decide whether we should reject the null hypothesis, and we want that probability to be small. We don't want it to be due to random chance. And so here 0.16 is much bigger than 0.05, so I don't have strong evidence to reject. If it was a one-sided t-test, well, I'm not going to have these two things here, these two shaded areas. I'm going to only have one shaded area. So that's about half of the total yellows. I only have one. So I'm just giving you some diagrams. The p-value is the area under the curve or the amount of simulated data to the right or left of that line. And it's greater than if it's only one-sided. So I'm going to get half the area. How do I use the theory-based inference app? It's bizarre. There's no directions on there, so I saw people were struggling. And in fact, I was recreating over the weekend how you might have got a p-value of 1. You'll never get a p-value of 1. So if you get a p-value of 1, something went seriously wrong. So the first thing is this part of the app is not there. You only have this part. Your scenario is that you have one mean because you're looking at sample means, so you choose one mean. I forgot what other selections there were, but you choose one mean. Your sample size was 100. Your sample statistic was 3.01. And your sample SD was 1.97. Then you select this test of significance. You need to check that. And this side opens up. You set mu equal, you put your null and alternative hypothesis. There's other choices here. There's a greater than choice and less than choice. And then you hit calculate. And that gives you the standardized statistic. In your book, there's a table that refers the standardized statistic to strength of evidence. They're similar to p-values. The p-value tells you everything, though. It tells you that there's not strong evidence because p is equal to 0.1899. That's not smaller than 0.05. So there's not strong evidence for not rejecting this. There's not strong evidence for rejecting that null hypothesis. Some of you said that it means that the null hypothesis is not true. That we can never say. We only have strength of the evidence. There's not strong evidence to do it, or there is strong evidence. You can never say it for 100% sure. And I actually explained this to one of my colleagues once, that a p-value not being below 0.05 does not mean that the null hypothesis is true. It only means that the strength of evidence is not there for me to reject it. That's what it means. And so you have to be careful. So this is the sample size, and then select this test of significance, enter your null and alternative hypothesis, and you'll have to switch those symbols to not equals here. And then the t-stat and the p-value are down here. Now what I want you to do is, if you got this incorrect, the simulation-based one, I want you to change this to greater than and answer the question of, what if the Cal Poly students in my sample, are they watching more TV? So then you would choose greater than. You should get different numbers here than what I got. So I just want you to run through the same example, but with greater than, and see what happens. The last one was, how do you do the theory-based normalized statistic or standardized statistic? Well, I got 1.32 here. Over here, I already know that the p-value associated with it is not strong. But there is a table in your book, and I couldn't find it. It was a Z table that had just the Z cutoffs. Z and T are the same as far as you know. So for your book. So you could go to the book and find that table where it has, in fact, I would flag that table if you find it, because that gives you the cut point values for strong evidence versus non-strong evidence in terms of the Z statistic or T statistic. They're one and the same for you. Other notes that I noticed on here, the Greek letters are used for parameters, or Sesame Street letters are used for statistics. Statistics are calculated on the sample, they're calculated. Parameters come from a process like flipping the coin, or they're just known from the population. I had some definition table comments so far. My suggestion is keep the central limit theorem simple. If you record enough sample means, eventually the sample means, the frequency of those sample means, if you made a dot plot of those sample means, it would make a bell curve. Remember my example that I showed you with the average number of heads and a flips of a coin? You could see that eventually, if I just kept doing this, those sample means ended up becoming by themselves a bell curve. And the mean of that bell curve turns out to be the population mean. So that's the theory we're using that justifies making a simulated null distribution and grabbing that and then using that kind of theory. A few of you got the definition of resistance statistic wrong. It's one that doesn't change due to outliers. So there's not a few A's that can change the grade. An example of a resistance statistic is the median. Whoever's in the middle, even if there's a bunch of A's, they still stay in the middle. The midpoint's the same, even if you have those A's in there. The average is not. If you have more skew towards the number of A's, then it's going to pull that average up. And unfortunately, that is how curves are made. So if you have 5 people in 100 that make all A's, they're ruining the curve for you, which we don't have here, but just so you know, that's why people were angry at them. So they did understand some statistics. For histogram, I would explain a little bit more than what you have there so you remember what those dot plots are. It's a graph where the x-axis is whatever you're measuring, like percent heads and 10 flips, and the y-axis is the number of times it ended up in that bin. So every time you do 10 flips, and here's where I say there's an example. I need an example to keep this straight in my mind. Suppose you have 100 plebes, and they're flipping coins. Each of them are flipping a coin 10 times. Then you would end up an x-axis from everything from 0 to 100%. If a plebe ended up getting 20% heads in their 10 sample, then you put a dot in the bin labeled 20%. If another plebe got 30%, you'd put a dot in the 30%. If a second plebe got 20%, you would put 2 dots in the 20%. You keep putting dots there and keep a count of how many people ended up getting 20%, and that would make the 20% spike. What's going to happen if you have 100 plebes doing this is you're going to see a big spike around 50%. And that's what a dot plot or histogram is. All right, I hope this helps you with the problems that you have to redo, and I hope it also helps you for the midterm. I think homework like this is really important because it gives you a feel, it gives me an understanding of where you're at. So if I just assumed you got it and drove on, well, that's not true, is it? And so let me know if any of this you need more help with, and I will.